Welcome to The Explainer. Today, we're diving deep into the story of one of chemistry's most fascinating compounds, nitric acid. We're going to cover everything, from how it's literally forged in lightning to how we make it on a massive scale. So, let's get started. So, get this. It sounds like something straight out of science fiction, doesn't it? But it is 100% true. Every single time you see a thunderstorm, the sky is basically running a huge, powerful chemistry experiment. All that energy from a lightning bolt, that's the first step in making nitric acid, right up there in the atmosphere. Okay, so how on earth does a flash of lightning actually cook up an acid? Well, it all starts with the air we breathe, which, is mostly nitrogen and oxygen. Now, these two gases usually just mind their own business, they don't really interact. But a lightning strike? That changes everything. Let's break down how this happens. It's a three-step process. First, the crazy heat from the lightning forces that nitrogen and oxygen in the air to combine, forming nitric oxide. Then, that nitric oxide links up with more oxygen, creating nitrogen dioxide. That's a brownish gas. And for the final step, this gas dissolves in the water droplets in the clouds, mixes with a bit more oxygen, and boom, you've got our star of the show, nitric acid. So that's how nature does it on a grand scale. But how do we do it in a much more controlled setting, like your school chemistry lab? It's actually a pretty straightforward process, but you have to be really, really careful about the conditions. Let's check out the recipe. The ingredients are pretty simple. You start with a nitrate salt. Could be potassium nitrate, could be sodium nitrate, and then you react it with concentrated sulfuric acid. Now, the sulfuric acid is the key player here because it's what we call less volatile. That just means it doesn't want to turn into a vapor very easily. That stability lets it push the more volatile nitric acid right out of the salt. And here's what that reaction looks like. The sulfuric acid basically hands over a hydrogen ion to the nitrate, and that's what forms the nitric acid. The leftover bit is potassium bisulfate. It's a classic displacement reaction. You've probably seen those before. But to get it to work just right, there is one super important detail we have to control. This right here is a classic exam question, so you'll want to pay close attention. The procedure is super strict about keeping the temperature below 200 degrees Celsius. So why that specific number? Why is it so important? Here's the deal. If you let the temperature get above 200 degrees, you get this hard, glassy crust of sodium sulfate. It sticks to the glassware and is an absolute nightmare to clean off. On top of that, at those higher temperatures, the nitric acid you're trying to make starts to decompose. And you'll notice the mention of an all-glass apparatus. That's because those nitric acid vapors are so corrosive, they would just chew right through a rubber or cork stopper. Okay, so making a little acid in the lab is one thing, but what about the huge amounts that industries need? For that, we turn to the master recipe, the Ostwald process. This process was a total game changer back in the early 1900s. It made the mass production of fertilizers and explosives possible, which completely changed both farming and warfare. The Ostwald process is really a three-stage journey. It all starts with the catalytic oxidation of ammonia. Then, the nitric oxide that gets made is oxidized again. And finally, that product is absorbed into water to create our nitric acid. Let's look at the details for each stage. All right, this table here is basically your ultimate cheat sheet for the Ostwald process. Stage 1 is the really hot stage. You use a platinum catalyst at around 800 degrees to turn ammonia into nitric oxide. For stage 2, things cool way down to about 50 degrees, and that's where the nitric oxide turns into nitrogen dioxide. Finally, in stage 3, that gas goes into an absorption tower, packed with quartz pieces, or it's mixed with water and oxygen, to give us our final product, nitric acid. So we know how to make it, but let's talk about what nitric acid does. If it had a chemical personality, its most famous trait would be that it's an incredibly powerful oxidizing agent. But what does that actually mean? Simply put, an oxidizing agent is a substance that causes something else to be oxidized, which really just means it's great at stealing electrons. Nitric acid is a champ at this because it's a bit unstable. It breaks down really easily, and when it does, it releases a single super-reactive oxygen atom. We call this nascent oxygen. You see it written as an O in brackets, and it is the secret to nitric acid's incredible oxidizing power. You can really see this power in action when it goes up against nonmetals. For instance, it can take solid carbon and oxidize it all the way to carbon dioxide gas. It can even take something like sulfur and oxidize it to become sulfuric acid. And in both of these reactions, you see those classic brown fumes of nitrogen dioxide being produced. That's your clue that the nitric acid itself has done its job and been reduced. So, with all these different chemicals floating around in a lab, how can you be absolutely positive that a solution has a nitrate in it? Well, there's a classic go-to test for that. Think of it as the secret handshake for identifying nitric acid and nitrate ions. It's called the brown ring test. Here's how you do it. You take the solution you want to test and mix it with some freshly made ferrous sulfate. Then, and this part is really important, you tilt the test tube and very, very carefully pour concentrated sulfuric acid down the side. You want it to form a separate layer at the bottom. If there's a nitrate in your solution, this beautiful brown ring will appear right where the two layers meet. It's a really unique result, right? But what is that ring actually made of? What's the chemical that gives it that distinct brown color? Well, the answer is a little bit of a mouthful, but it's the key to understanding this entire test. And there it is, nitrosulfurous sulfate. It's a pretty complex compound that only forms right at that junction, and it's really unstable. If you shake the test tube, that ring will just disappear. Knowing this name and the formula is a major pro tip for acing any questions you get on this topic. All right, we have covered a ton of ground, from lightning in the sky to a little brown ring in a test tube. So let's do a quick recap of why nitric acid is so important, and then we'll test your knowledge with a few quick questions. So why does all this matter? It's simple. Without nitric acid, we wouldn't have the modern fertilizers that help feed billions of people. It's also the backbone for powerful explosives like TNT, and its influence extends into things we use every day, like nylon, plastics, dyes, perfumes, and even the beautiful etched designs you might see on copper and brass. It is a true workhorse of the chemical industry. Okay, first question for you. In that big industrial Oswald process, what's the crucial catalyst they use in the very first step? I'll give you a second. Got it? If you said platinum, you are absolutely correct. That platinum catalyst is essential for that first high-temperature stage. Question number 2. We really hammered this point home for the lab prep. Why is it so critical to keep that temperature below 200 degrees Celsius? The main reason is to stop that hard, glassy crust of sodium sulfate from forming, because that stuff is just a huge pain to clean off the glassware. And for the final question, what is the full chemical formula for that unstable compound that gives the brown ring test its name? This one's a bit of a challenge. The answer is nitroso-ferrous sulfate, and its formula is FeH2O5NOSO4. Seriously, great job if you remembered that one. And that's a wrap on our deep dive into the world of nitric acid. From its origins in lightning to the secret handshake of the brown ring test, you should now have a really solid grip on this powerful compound. You've totally got this. If you found this explainer helpful, like, share, subscribe, and don't forget to press the bell icon for more.